Good panel? Medium panel?
Go ahead.
Useless panel. I'm kind of sad that there wasn't a wall of paper for me to run through, but I did my pre-talk pump up, which involves running miles, really excitedly screaming about football. So if you saw me outside, I apologize if I scared you. So today, as it's been introduced, I'm talking about moneyballing, how to use data to win at fantasy football. Of course, to establish some credibility with you all, I should tell you who I am. And to immediately unestablish credibility with you all, I'm going to tell you that I have lied to you. I am not going to tell you how to win fantasy football. No one is able to tell you that. What I will tell you is how you can model what your expected outcomes are, what your aggregate risk is, and more realistically, I'm a database nerd, I really am, and so I'm going to talk a lot about data schema design. And so, who's really excited about data schema design? I am. So if I'm saying, thank you, exactly, I knew this meetup would love it. So, if I'm not here to tell you about how to win at fantasy football, and I'm fundamentally a liar, why would I even come here? Obviously, I'm just here so I'm Fantasy football, if you are not aware, is incredibly serious business. The Fantasy Football Lobby Association, based in DC to lobby Congress on behalf of fantasy sports everywhere in the US, actually exists. It is a thing. Their major point of what they do, from what I can tell, is it has a website that explains how fantasy football is not gambling and it is a game of skill. And I appreciate their service because this means that I can talk very easily about rich data sources that are actually fundamentally like gambling, which makes any probabilist/statistician at heart get really excited, right? Statistics came about by old French dudes sitting around trying to figure out how to beat each other. And so, when I think of football in that light, I get really excited. I was not into football before I realized that there's so many cool data modeling problems in there. This is not a commonly said thing. So, fantasy football, serious business. The NFL makes billions and billions. And if you compare the fantasy sports industry to the NFL, it's about 10% of that, which is enormous. And so, even if you are not interested in playing fantasy football, you have other options to consider. You don't have to enter a league. There are places out there that will insure your fantasy sports picks. I've even heard there's options trading on fantasy football players. You can go crazy. You can create your own crazy little market for fantasy sports. You don't have to do this with football. Obviously, March Madness is coming up. Get excited. In preparing for this talk, I kind of realized that not everyone that is excited about scalability and database schema design and predictive modeling maybe necessarily knows what fantasy football is. So bear with me while I explain. You see, every year the NFL gets together, they have players, they play some games, and we can watch that. Usually watch this from a TV, but we can also ingest these data sources and try and think about what it means to create our own imaginary fantasy even teams. So in fantasy football, you get a bunch of friends together. You take turns drafting players. There's usually some sort of mechanism for some sort of equity in how you're going about drafting players. Sometimes there's a salary cap. And so a different problem that I'm not going to talk about here, but it's interesting, is how do you optimize for a finite salary cap? What sort of players you're going to draft? Then there are many variants of how these rules are played. I'm going to talk about the version that I use to do this model. Essentially, you have a pool of players that you can choose to play as some subset of every week. And you watch what they did in their actual real NFL games that week. Given what they did in their actual real NFL games, they get assigned fantasy points. Those fantasy points are cumulative over your team that you played that week. And depending on how the league is structured, you can win games against competitors, or you can have a cumulative total that helps to win the season. So, if I'm actually really secretly excited about database schema design, why did I choose fantasy football? The answer is that it's not this. What I mean is that when I think about really hard problems involving complex data types and entities, and I'm going out there and trying to find a good data source to talk about that doesn't give people this really creepy feeling, there's not a lot of them. So I work for a company called Cloudera. We make some distribution of Hadoop. And people use Hadoop to deal with huge amounts of data. And usually, very, very frequently, some variant of a view on this huge amount of data is an entity that they care about. So these could be like users or customers, and they're doing different things. So they're like calling call centers, clicking on websites. They have these complex time series, lots of sort of strange features attached with each of these events. And they need to figure out how to store this correctly and access it for analysis. These data sets about people don't exist publicly. It would be really creepy if I could actually get my hands on them. I would be weirded out by that. And so I spent a long time thinking about how to access a good data store. And I realized, and it's actually partially Trey Causey's fault, that football is a great, great data source for this. These people are used to being watched on the field, all of their movements being recorded. So I'm going to make an argument for why this is not necessarily actually a creepy thing to do, keeping complex event histories of individuals. I myself cannot get access to this data, but I freely give this sort of data to people all the time, so I use Mint.com. Mint has my profile information. They know a lot about me. They know a lot about my savings account. They know a lot about my checking account, know a lot about my 401k. And in abstract, that's really creepy, but that's something that I trade for a service that I see as really valuable. So why did I choose fantasy football? It's not this creepy spider robot climbing over the city. Short answer. So, as I said, I'm really excited about data modeling. Why would I talk about data modeling at all? So I claimed that, I'm interested in this because customers of Cloudera have a lot of data, and often it's in this entity complex event history form. Okay, who cares? There's two 500-pound gorillas in the room. There's a, soulful gorilla on the right, who I'll call dimensionally modeled data warehouse. I'm going to briefen that phrase to data warehouse. There are a few different kinds of data warehouses. Let's go with dimensionally modeled data warehouse and just save me some breath. I'd really appreciate that. And on the right, young forlorn gorilla, that is the 3NF. So these are two useful ways and schemas for modeling data. Why would I care that why would I think that there might be something else to discuss here? Well, the answer is that these two different data schemas are engineered for different workloads. So a 3NF schema is the type of thing that you expect to support a back-end application. So 3NF schemas are designed to have no repeated data inside. So this means no data duplication. So if I go to write something or do an atomic transaction, this can complete really quickly. I don't have to go to a few different places in my database and update that entry. Great. So for application backends, this is generally wonderful because you get low latency CRUD, and if you're a developer, this is what you care about. On the other side, which is probably closer to where analysts want to live, there's a dimensionally modeled data warehouse schema. So dimensionally modeled data warehouses, if you've not interacted or experienced them yet, they're designed for easy per-key aggregations. So what this translates into, you can imagine being a multinational retailer. You have a ton of sales. And these sales are the types of things that you're probably going to want to add up with different keys or do different per-key aggregations. So let's say you have a giant table in your dimensionally modeled data warehouse that has all of your sales. And then you have these tables coming off of it that identify interesting sort of nouns associated with those sales. So those nouns could be the states that they were sold in. They could be a user identifier or a customer identifier. These dimensionally modeled data warehouses are designed to make it really easy to do joins and per-key aggregations. And this, if you hear per-key aggregations, I think you immediately think BI reports, nice dashboards, things like that. And the really key, beautiful thing about dimensionally modeled data warehouses is that they have conformed dimensions. So conformed dimensions means when you have a noun that you're thinking of, so like the state of Maryland, there is one way to refer to that noun. Think of normalizing addresses where you have MD or MARYLAND and so on. So this is one of the biggest advantages, I think, for analysts when it comes to dimensionally modeled data warehouses, is that you have one noun to talk about everything. And this is actually a huge stumbling block when you begin to put all of your data in one place and try to join customers together. So, let's say you have your call logs, you have your clickstream logs. What if you don't have the same ID for these people? This is something that's a huge goal that should always be strived for. So these are two different workloads that I claim are wonderful, useful, have their place, and will always be the 500-pound gorillas in the room, but do not necessarily work well for complex entity event history modeling. So, why? This is where I share one of my favorite personal stories, and that is I was dropping out of grad school. I was going to go work for a big data company, and they were building a NoSQL real-time machine learning model application platform on top of HBase. I called my father, who is a database administrator, and I tell him that I'm going to go work with HBase, and he just sighs. He's like, Juliet, really? NoSQL? Yeah, sorry, Dad. So, now, having a few years of experience in the field, I actually have a good response to that. And that is, Dad, it's not NoSQL. And that's pretty obvious given the number of SQL query engines that exist today. But what it is no joins. What we really mean when previously we used to say NoSQL means like, you should really be careful with what you're joining together. So, why is that? I think that there are two types of clusters. There is a good cluster, there is a bad cluster. Good clusters, to me, do not spend a lot of time shipping data over the network. So there's a few things that are slow that if you're working in a distributed environment, right? One is disk I/O. You're always going to be rate limited by if you have disks that actually spin, how fast it can spin. And the second is sending data across the network. Network switches are incredibly slow. The more data you send across, the worse it is, right? So, to me, a good cluster is one that you operate in such a way that it does its data processing with the data. So you have your data right there, crank on it, and you're not sending a lot of information across the network. When you get to complex entity event histories, neither 3NF or a dimensionally modeled data warehouse give you the ability to avoid sending information across the network if you want to do per entity calculations. So per entity in a football case it would be per player. And that's really the reason that I think that it's worthwhile to talk about what it means to do data modeling in a distributed environment when you're interested in entities that have these complex event histories. So if you are really sad that I'm not going to tell you about how to win at fantasy football, this I think you will thank me for, despite me not actually telling you how to win. This is an amazing, amazing data set. It's called armchairanalysis.com. And I think the whole image of a football and a database part is absolutely true. I am completely impressed by this data set. So the data that I'm using in this presentation today is every play made in the NFL in the last 14 years. I'm excited about that. I'm really excited about that. I think it's amazing. During the season, it's updated every week on Monday, Tuesday, and so you can keep your analysis up to date with what's going on. If you are using it for personal purposes, as I imagine you are, it's $30-ish, which is probably worth it if you're really into fantasy football. I bought the commercial license, I promise. And sent an email to the guy I think it's one guy that just makes this happen. And I don't know how he does it, But I sent an email to him telling him that I loved his data set and I wanted to use his logo, and he was like, use it everywhere, tell everyone about it. Done. Totally sweet data set. There's a lot of information in there outside of plays. We have a little bit of information about players, like where they played in college, their height, their weight. Have some information about where games are played, the weather, the wind direction. I know, possibilities are endless, right? So, amazing data source. I'll talk a little bit about how we actually get this data. So there are two mechanisms. One is a pile of CSVs. I like my data neat and organized and not in 30 CSV files. Which is great because along with these CSVs that they provide, there's also a little PHP script that you can use to load it into MySQL, and you get a SQL database. This I can deal with. Okay, SQL databases at types. Very reasonable. I can kind of try to infer how these things might be related. There's a data sheet that comes with it. But this database is in 3NF format. And so now put yourself in my shoes and think about, oh, I found this data set that I want to use for complex entity event history, and I'm going to pretend that it's huge. What if this data set, what if actually every person in the US played in the NFL? I think we'd all walk around with a lot more black eyes and injuries, but we would then have a very huge data set where this might be pertinent information. So bear with me while I talk about why 3NF is kind of complex to use in these analysis situations. With small data, you can join tiny tables together, and it's not a big deal. With big data, joining big tables together is a very big deal. So we'll talk a bit about what data actually comes up here. So 3NF, I can understand why Dennis, the guy that made armchair analysis, used this format. For him, as an application developer, him being an application, well, the application being something that ingests football data and then gives people more data about football. I can see why he wanted to use this. He only has to update things once. It's easy to track what you're appending, and it's a simple thing to update. Like I said, simple, fast CRUD operations. This is a deeply annoying format for data analysis, I think. The reason that I think this is deeply annoying is that these lines that I drew that sort of showed what tables are connected, so players are connected to different types of plays, games are connected to plays. I had to sit there and figure out what keys might actually line up correctly, which keys might actually be referring to the same thing. And so while there are, well, that's not the right way to put it. While every thing has a unique identifier that is associated with it, you still need to think hard about how all these tables are related. So, my initial next reaction would be, well, we should put it in a data warehouse. Data warehouses are meant for good, easy, per-key aggregations. It puts all of your information about a player together in one place. So what would I do if I took this 3NF database and I decided to put it in a data warehouse? So, as I mentioned, dimensionally modeled data warehouses have facts in the center, so these fact tables that are full of numbers that you might want to add together. And then coming off of them, they have nouns with sort of not very quickly changing descriptors. So let's take an example of pass plays. So passes are information of numerical pieces of information about the passes that live in the center table. And then we might want to know what passes are related with players, or what passes are related with games, or what passes are related with different teams. Because this might be different ways we want to slice our data to understand what it's doing. This is pretty nice. It gets us kind of close. We can do easy aggregations, but if we are storing these as different tables in Hadoop, these will end up being actually different files in Hadoop, which will live in different places of the cluster, who knows where, and trying to put together this pass data with the player data, or pass data with games data is going to be a join or two joins. And NoSQL means no joins, or at least please avoid trying to do joins, because it's just going to be slow and you're not going to like it. So I'm not here to bash on dimensional modeling. I think dimensional modeling is amazing, and I think there's actually a ton to learn from it that if you don't learn from it, we're just going to make the same mistakes that people made 20 years ago until dimensional modeling for data warehouses came about. So this is my favorite data warehousing book. I think you should read it, and if you read it, you will profit. It works through some very concrete examples about how to do dimensional modeling. I'm very lucky, and I get to talk to the guy who wrote this, Ralph Kimball, about my ideas around this stuff. And so I've vetted it with him, and he doesn't think it's crazy. I feel good about that. So, well, okay, we have this 3NF. We know that this certainly would be a lot of joins to get all the information we might need together in one place. Dimensionally modeled star schema would also be a fair number of joins with large tables. So what do we do ahead of time? So let's say we have players, this core table that can be used to join against the tables out to the side that have specific and different types for the features that are in there. So different information for punts versus blocks versus conversions. How are we going to go about mapping this onto something reasonable? Well, the way that we avoid joins is by joining before you really need to join, right? And what I mean by that is, okay, well, let's think about what we need at the time of analysis in order to do our computation correctly without any joins. So in my case, let's say we're just interested in what players do. If we're just interested in what players do, then the per unit piece of prediction is going to be a player, and we're going to need every piece of information that we have about that player. So in this case, what we're going to do is we're going to take that player table, which has some descriptions of this person's name, this person's height, and this is going to be a kind of like static single record. And then we're going to take these other multi-event tables, so there could be multiple plays in the core table that when you join it with players and punts, so if a player has multiple punts, you join the players table and the core table and the punts table together, and you're going to get like 10, 100, 1,000, or 0, I don't know, we don't know what the player we're talking about, I guess. But we're going to take all of the rows in the punts table that are associated with that player, and we're going to make a series of records and think of those as a column. So instead of thinking about a flat rows and columns, you're getting a little bit three-dimensional. And so we map all of these dimension tables, which are the things that describe the nouns, so the punts, the blocks, the conversions, the tackles. Oh, I've done this the wrong way. No. So the punts, the blocks, the tackles, and conversions are the facts. And the yellow tables are the dimension tables. Yes?
Real quickly, do you also include all the meta information about which punt took place, like which game, which team they were playing for, etc.? Does that also go along with each one of those separate little nodes?
Yeah, so this is something that...
Can you please repeat the question?
Oh, yes. So your question was, do you also record the meta information related here? So meta information meaning, can you give the examples again, actually?
Well, I mean, these are all connected to each other by which game they happened in, which team the person was playing for. There's all sorts of connecting information about these different nodes, and once you break them down like this, you sort of lose that phase information about what's going on, how to connect it, how you do it.
So the question is, how do you preserve information in related tables? So I think the answer is somewhat simple, that if originally you could join these two things together and you have the keys, as long as you don't throw away the keys, you can always go back and join. You're not prevented from joining, it's just a bad idea. I mean, not always, but I like to tell myself that. It's a terrible idea, don't join. But as long as you have keys that can be related, you can always take a data set that you had somewhere else. But this is an excellent lead-up, eventually, to why this schema almost kind of, but doesn't quite work, and how it changed a little when I did this analysis. So what we're doing is we pick the unit of analysis, we think about all of the facts that are associated with it, and we take any of the rows in those fact tables and think of them as a series of records inside of a column. So like kind of three-dimensional, stacking post-it notes on top of each other. So we're going from the star schema and just collapsing it into a single dimension, or multiple dimensions, which I will talk about why that might be useful. And I work for this guy that's kind of clever and kind of funny, and he came up with what I think is a both silly and wonderful name for this, and that is a supernova schema, which is a collapsed star schema. He was a little annoyed when I, as someone with a background in physics, pointed out that not every supernova actually happens by a collapsing star. And he just ignored me, which is fine. It's still a pretty great name for it. I'm going to go with it, mostly because I get to use images like this at a talk. So you're welcome. So I think I made an argument here for why we need a supernova schema, or why I need some schema that's not 3NF, or not dimensionally modeled data warehouse, because joins are gnarly, especially if your tables are very, very large. So, well, given that we want to do that, how? Why? What are we even doing? How would we do this? Exhibit. And this is both cute and clever and fun, and I'm going to be perfectly honest with you about why I ended up using Exhibit here. Originally, I was going to do this all in Spark. And then it was the weekend before the talk, and the file still was empty. The job ran, nothing got written. I was like, oh, no, okay. We're going to do this, we're going to put it together. How do I do this fast? What works? Which is an important question. What works? And the answer is Hive works. I used to not think very highly of Hive. I love Hive now. I don't know what to say. I love Hive now. It's slow, but it works. And it handles complex nested records very well, which is something that Impala currently does not, but if you are interested in complex nested records in Impala, there is a design document with goals out there, and this is features that are getting put in, which I'm really excited about because Impala is way faster than Hive. But I only use Impala part of the time because I like complex nested records, and so the point is, I decided to use Hive. I got real excited about Hive. Really thankful for Hive, too. So, I used Hive because I wanted to use complex nested records. The current API for that is actually not that fun. And so, I used Exhibit, which is SQL inside of your SQL. So you can SQL. Body SQL. Which I think is a pretty clever name. So wait, I just said, okay, the API is kind of gnarly. I use this thing called Exhibit instead. So Exhibit is a collection of Hive UDFs, user-defined functions, which lets you write SQL queries on those columns that are repeated complex nested records. Let's talk about what that might look like. So, how are we going to go about making a Hive supernova table? So like I said, I have these, you can imagine the 3NF diagram that I had. I just mapped that onto files in HDFS. And then, given that I have files in HDFS that follow the schema that I sort of simplified and described about football players, I want to make a supernova style schema like I described, where I have per key complex repeated records. So, an important thing to recognize here is that once I have these joined together, every input record, when I'm doing some sort of map reduce job or what have you, is going to come all at once per key. And so if I'm interested in overall what a player has done ever, then player as a key is a great choice. But if I'm interested in how a player is evolving over time or game to game, then it's probably a really good time to think about composite keys. And so this begins to touch on your question about how do you fold in outside information. And I think that there's a distinction. There's the outside information that's pertinent and not pertinent, or at least immediately for what you think of your design goals. No schema is perfect. That's why we have schema migration software, right? Lovely, lovely flywheel. So in this case, we have players, going to be one of our keys, and we're also interested in how they're changing game to game, which is another one of those dimension tables, right? So dimensions end up being keys in supernova schema land, and facts end up being these complex, nested, repeated records, where you can think of each column here, where you can think of each column as having the same schema as the table that it came from. So punts is going to be a complex record, where the record has fields like PID and punter and pgrow. Now I'm going to build it out again. So we're going to do a select, which says, okay, here are going to be my keys that I'm using, and then collect all, which is one of those UDFs that's defined inside of exhibit, where I say from football.pass, I want you to get all of those records and call them this. So from football.pass, get the play ID and call it play ID. So we're making a collection of named structs, which kind of, if you squint, looks like a tiny little table. So what does this table look like after I use that UDF? Well, if I describe the table, I have my two key elements, so my player ID, which is a string, and my game ID, which is an integer. And then I have this interesting column, which is an array of structs that are named and have the same column names as the fact table that I grabbed them from. That's convenient. It almost looks like it's a tiny table inside of a column. And that's pretty much the key, is if you have repeated records that are the same type, have the same schema, it's like that column is like a tiny table. So if we have a table whose columns also have tiny tables, what syntax are we going to give to people to allow them to write SQL queries on those tiny tables? Well, so this is I'm creating a table in this query, but the select part is the interesting part of the query, probably. So from my fancy complex nested records table, I want a lateral view within, which is just our special keyword. If you're not familiar with views. So lateral view within this table, and then I pass it an array of SQL statements that I want it to apply to that column, which is so nice. So what I'm doing here is actually going from a record of passes to computing what the fantasy points were for that player in that game, broken down. In this one, so in this one, I don't think I break it down by how. Oh, yeah. I don't break it down by how those fantasy points are happening, because this is 4 passes. But there's three different like classes of fantasy points, and then the totals end up coming together. So the 3 different fantasy points that you can get are from passing, rushing, and receiving. I thought it would be interesting to break it up this way. Never actually used the fact that they were broken up, but I could. So I've modeled my data. I have the supernova schema where we used to have a dimensionally modeled data warehouse. We collapse this together, and we have per entity, where in this case our entity is actually a player in a game. And we can try and think about what we would do there. And so if you're here from the modeling part of this, is what I'm talking about. Oh, no. There we go. So what do we want to predict? I claim there's actually probably a lot of things you want to predict. Directly predicting points is probably going to be pretty hard. But in aggregate, it might get easier. So, okay, let's give that a try. We know that as a fantasy football team manager, we want to maximize our points, and we don't want too much variation when we're making a guess about who might do well. So, okay. Historic fantasy points are easy to calculate. I did it with a bunch of SQL statements and some SQL inside of SQL statements. This seems like a relatively straightforward problem, at least in the sense that I can call it a regression problem. So, okay, we have like actually a very tough regression problem in front of us, but it's a regression problem, so let's start really simple. Do the most simple autoregressive thing you can do. Why would I do that? Well, I feel really weird predicting things if I don't know what the stupidest thing I can do is and how well that performs. Because if I can't outperform the stupidest thing, I don't have a baseline to compare it to, right? So, start with the stupidest thing, which is, Okay, we'll predict that they will score the average number of points per game that they scored last year. Okay, that's actually not a bad heuristic. So, if that is what we're trying to optimize and how we're going to do this regression, well, how do we think about risk? Well, let's go with standard deviation and points scored. I think that there's some oddities in this definition, and this is actually the definition that's used in portfolio optimization by finance companies. Standard deviation is symmetric around the mean. That's weird. I don't really care if my team scores more points. Is that risk? It is at least a measure of variation. So, as I talk about this, it's actually relatively easy to replace both of these definitions, both of the thing you're trying to maximize and what your definition of risk is. And how to aggregate that might become more complicated, but you can change this. And so if you're thinking about this, then understand that this is simple, it's modular, and you can change it. So, like I said, my predictor is the expected number of points in 2014 are going to be the expected number of points in 2015. From this simple predictor, we can also, well, not from this, we can also define the standard deviation from last year and use that as what sort of risk you think they have this year. Probably not the best predictor. And then for each roster, I want to figure out how to aggregate expected points, easy, add it. And then I want to figure out how to aggregate risk. Again, if we assume that the covariance isn't anything, then we can just add it and it's fine. Whether or not the covariance is 0, you know. Statistics is an art, that's what I like to tell myself. So, great. We know how to take a bunch of players, put them in a roster, figure out what their expected total points are, add it. Figure out what the expected risk is, add it. How many rosters are there? A lot. It's 10 to the, well, I actually don't even remember the preceding number, but it's 10 to the 25. And me being the type of person I am, I computed that and I was like, I wonder what Spark would do if I made it try to do that. And the answer was actually pretty great. It did a wonderful job of spilling to disk, chugging along. It killed the web UI, which was unfortunate. But other than that, it just knew that it had, well, I mean, it didn't know it when it was going to stop, but like it knew it was just chugging along and eventually killed it after a while because, you know, I don't have to drown that many polar bears to understand that this is going to take a long time. So, given that I had exhibit how I'm going to compute per player predictions, this is actually an incredibly boring query. I don't even know why I put SQL queries on the page. Do I expect you to read them? I'm sorry. I'm sorry. I'm running out of time, so I'll show you guys some nice pictures. So if we take a look at the plot with the expected number of points and standard deviation, we can see that, as we expect, the variance increases as the expected value increases, so as the average number of points does. If you are looking at these plots and you're like, wow, those are really pretty plots, they must have taken so long. They did not. They were 2 lines of Python code in a library called Seaborn. I love Seaborn. If you haven't tried it, you should try it. It was literally 2 lines to make this wonderful plot. I was just pleased when I saw that this was this easy. So, nothing here is actually that interesting. Other than recognizing that, yes, as the expected value increases, the variance increases. Quarterback land, a little more fascinating. I think from this, you can see which quarterbacks play a lot. This little group over there. There's a little bit of structure to this, and you can guess that as we begin to aggregate these expected values and risks together, that the shape and structure that we see in some of these, like you can kind of see distinct blobs, right, begins to go away. So over here, probably won't actually be able to see it. This is a sample of some of the rosters. Obviously not all of the rosters, that'd be a really hard image to make. But you can see that a lot of the structure, again, gets lost as you begin to add up all of these groups together. But this is really the only sane way that I could imagine beginning to visualize this data, because like, if you have a point, you want to know where that point came from. So I made a cute little graph that lets you see who WR-1 is. So, yep, my model is simple. It's kind of the dunce in the corner. I always start with the simplest plausible model. After, if you tried any other model, you could probably estimate its variance similarly. So, you know, my regression algorithm is silly. But there are a lot of really sweet ones out there. Figure out your favorite regression algorithm and use it. And also, if I had a model that did work, do you think I would tell you? I think I'm beginning to run out of time. I'll give you a brief description of this last part. Keep your team bored. So where does risk come from? I don't think risk is actually realistically related that much to variance in the previous season. Probably a little bit. But it seems, from talking to very serious fantasy football players, that where they see risk is in injuries. And injuries, again, unlikely events, but they happen, and it's very hard to predict when they do. So it seems like this is one of the biggest risks for fantasy football teams, or like for your fantasy football team, what if this person gets injured? Can we quantify that? Can we justify it? If you're interested, all of the data, all of the code used to analyze this data is on my GitHub account. You can see the Spark job that doesn't work, and if you fix it, I will, I don't know, probably send you a Hadoop yellow bear or something. Elephant. More interestingly, the things that do work, the exhibit queries, and a few IPython notebooks, one of which scrapes injury data off CBS.com, I think? CBSSports.com. And begins to do some analysis around how injuries affect players in games. And because we have per player, per game fantasy football stats, it's easy to join together. Fun and exciting.
Did you say it was easy to join?
Well, yeah, because this data is actually tiny. It easily fits on my computer. There's a bunch of photos, and here's a link to where that repo with the code in this goes to. And if you're interested in an exhibit, there's another link down there, which lets you do SQL inside of SQL. So you can query while you query. So, given that you're really pumped up to go win at fantasy football and or supernova schema modeling your complex event histories, what are your next steps? If you're on the football track, then you should get some NFL data from armchairanalysis.com. You should definitely read Dimensional Modeling Toolkit. You should probably think about it and figure out a plan, and then profit. You're welcome. Ask me for business plans anytime. Thank you. Are there any questions? You first, maybe. Yes?
So this is just me being curious, but how true is it that somebody's points from last year is a predictor of what points they'll need for next year? Like, is that how close to reality is that?
Did we win 2 Super Bowls in a row?
Still feeling a little sore.
Only one pass.
Highly mediocre predictor.
I was wondering, the ML in Spark has some, regression algorithms for which are the users.
So MLlib has logistic regression, and I think one other more numeric, not categorical type of regression. What I will be doing next is actually using the H2O sparkling water interface. From MLlib, I think is great, and that is a completely different talk. But it currently has one type of algorithm for every algorithm type. So there is one way you can do regression. There is one way you can do classification. It's not as full-fledged. Using this as a fun example for me to work with data and Hadoop tools, even though it's not necessarily required, I'm more interested in trying to use H2Os. It seems that they have a much larger selection, and in particular, they have gradient-boosted regression trees. And I think gradient-boosted regression trees would actually do a much better job than really, really simple auto-regressive models. And so, no, I haven't tried MLlib on this. I think it's potentially a good choice, but it has one implementation.
Wait, so what did you use instead of MLlib?
Oh, yeah, I did auto-regressive stuff, which I just did in SQL.
Okay. So you haven't benchmarked it like against sklearn or R?
No.
MLlib.
Well, what do you mean benchmark what against sklearn or R?
I'm not convinced they'll all give you the same answer right now.
Oh, sure. Other questions? Yes.
Can you actually go back a few slides to GitHub?
Yes. Is that one? Other questions? Yes.
I'm curious if you have any speculation as to how Nate Silver is approaching this, because he seems to be looking at, rather than risks, at kind of edges and factor analysis, kind of the old school investment approach. And I'm curious, it seems like machine learning is obviously a huge problem, a huge solution set. How would you inject sort of domain expertise like a Nate Silver has to address this problem?
So, this is actually why I mentioned other types of economic activity around fantasy football. I think fantasy football is one way, and this is maybe somewhat tangential to your question. You should repeat the question. What this gentleman asked was, how do you incorporate expert knowledge, and then mention Nate Silver's approach, which is sort of classic financial modeling applied to football. Is that a good description of your question?
Edges.
Edges. I think making direct predictions of points is going to be hard, particularly in fantasy football where you're looking for the long period of time. Thinking about other economic activity around fantasy football, I think, is an easier way to begin to incorporate expert knowledge. So, for example, if I was a fantasy football team insurer, it would be a huge competitive advantage for me if I could figure out before everyone else if a player just got injured. I think there's lots of signals out there to figure out if a player just got injured, right? There's really good Twitter accounts that actually have these things. There's sports accounts. You could take the news articles and try to do some sort of information extraction of them to see if they're talking about a player, and if they are talking about a player, are they talking about that player getting injured? I think that, so probably one of my favorite things about taking this talk around is that anyone that sees it gets excited about the different possibilities of how the data can be manipulated and what you can do with it and what you can be predicting. So I would say there are many ways to incorporate expert knowledge, and I think you already seem like the type that can be pretty creative with it. So yeah.
So it'll be available afterwards for drinking?
Yes.
Everyone give Juliet a hand.